My name is Zhixing, a third-year master student from Department of Information and Communication Engineering, Tongji University. The title of our research is a dynamic transmission design via deep multitask learning for supporting multiple applications in vehicular networks. I will present our work in 5 parts. The first part introduces the background of our research. The second part presents the system model and considers the transmission design problem. Then we develop the multitask learning-aided transmission design and elaborate a training process. Afterwards, numerical results present the performance of our proposed method. Finally, we conclude our research. Improving road safety, alleviating traffic congestion, and reducing energy consumption have become the major concerns in the development of modern road transportation systems. The intelligent transportation system is widely considered as one solution to these traffic problems. Allowing high-quality communication among the elements serves the key technology of intelligent transportation system. However, because of various quality of service requirements, limited spectrum resources, and dynamically changing channel feeding, efficient transmission design in vehicular communication networks is challenging. Efficient transmission design in wireless networks has been studied extensively in the past decades. They use the power control strategy to balance the desired performance of each link and the mutual interference between links. They use optimization methods to solve different targets, and the objectives range from minimizing power consumption to maximizing energy efficiency. However, these researchers only consider the channel state information, but in vehicular communication networks, there are various information and requirements. We investigate the resource allocation in vehicular communication networks. Transmission design is carried out based on both the channel state information in the physical layer and the queue state information in the MAC layer. Our earlier work studies the vehicular networks in which each link desires to deliver different types of messages, which have different quality of service requirements. Our problem can be formulated as an optimization problem under the constraints of powers and different quality of service requirements, which demands sequential power control in the vehicular communication networks. Applying the Lyapunov optimization theory, sequential power control in a dynamic environment is transformed into a new optimization problem that can be solved greedily. But it demands a large amount of computation because the iterative computing process is necessary. There are extensive research of machine learning application in wireless communication. After being properly trained by dataset generated using time-consuming methods, machine learning networks can rapidly infer the similar results. We borrow this idea and apply it to our research. In our paper, we consider a vehicular communication system that consists of power control problems and encoding action problems. We apply deep multitask learning to transmission design in vehicular communication systems. Next, I will introduce our system model. We consider a multi-user vehicular communication network in which two pairs of source and destination vehicles share the same spectrum resource. Messages generation and transmission are assumed to conduct in discretized unit time slots. Source vehicles execute their transmission operation at the beginning of each time interval. Through the information theory, we can calculate the achievable transmission data rate between source and destination vehicles. Each source desires to send two types of delay-limited messages, which have different characteristics and quality of service requirements to support different road safety applications. The first type of messages, termed Type 1 messages, arrive in destination vehicles periodically with a constant rate. They normally carry real-time status of source vehicles, like speed, position, direction, and so on. They should be transmitted immediately. The quality of service requirements means that the transmission ratio of Type 1 messages should be sufficiently high. The second type of messages, termed Type 2 messages, randomly arrive in destination vehicles, and they can be temporarily stored in the queue. Such messages can be those that support environment sensing or onboard infotainment applications. Different from Type 1 messages, Type 2 messages can tolerate some delay. The quality of service requirements of the Type 2 messages means that the queuing delay should not become unlimitedly large. Our research is to investigate how to maximize the transmission energy efficiency, which implies the ratio of average long-term aggregate data to the average of corresponding long-term total energy consumption. Except for the aforementioned quality of service requirements of two types of messages, the optimal power is limited in the constraints, and we should select the action whether to send Type 1 messages as well. The objective function has time average operations. The constraints of two types of messages have time average operations as well. It is hard to solve it directly. In our earlier research, we applied the layer plot optimization theory to further simplify the optimization problem. The final objective is expressed as a series of mixed integral optimization problems of each time slot under the power constraints. We can solve it through the concave-convex procedure algorithm. However, the algorithm includes the iterative computing process, and it usually takes a lot of time to achieve the final strategy. This may prevent the strategy to be conducted in an online fashion. Therefore, we consider applying multitask learning to tackle this problem. At each time slot, except for fixed transmission requirements parameters and optimization weighting parameters, we formulate the other parameters and the solution of the optimization problem as input and output respectively. The channel state information, which implies channel power gains, the queue state information, which implies the length of the queues, and the achievable energy efficiency are regarded as inputs. The opti-powers and the chosen encoding actions are regarded as output. Thus, we transform the solution of the optimization problem at each time slot into a mapping problem. The inputs consist of 9 values, and the outputs consist of 4 values. In addition, directly using them in the loss function may cause model training to mainly consider the impact of large power values, while small values, especially when the channel qualities of the desired links are good, are more important in achieving high energy efficiency. Therefore, we conduct a feature transformation process that takes the logarithm operation to transmit powers. The same operation is conducted on the channel power gains. At each time slot, we have two different problems need to be solved. One is power control problem. The power of each link at each time slot is a real value between the maximum value and the minimum value. We regard the powers as a vector consist of two continuous values, and it can be formulated as a regression output. The other one is encoding action problem, where each link chooses to send Type 1 messages is a binary indicator. We combine two binary indicators, and the vector form can be formulated as a classification output. Obviously, the mapping can be modeled as two neural networks, termed as single-task learning networks. One network serves power control problem, the regression problem. The other one solves encoding action problem, the classification problem. We can define the loss for different problems respectively. However, the structure of the single-task networks does not leverage the potential relations between the optimal powers and the encoding actions. Therefore, We apply multitask learning to handle this issue. There are two parts of hidden layers between the input layer and the output layer, namely shared layers and task-specific layers. The shared layers are used to learn the common information of different tasks. The task-specific layers are used to integrate information from the shared layers, learn the individual inherent characteristics. The loss of multitask learning is the weighted sum of all the tasks. However, how to define the weights is a question. The simple solution is to choose the fixed weights for different tasks. For example, we set both 1 in our experiments. Apparently, it is simple to modify. However, the inference performance of such learning models is often strongly dependent on whether the weights are determined properly. Tuning these weight parameters via grid search is a difficult task. For practical applications, having a loss function that automatically finds the weights for different tasks are much more attractive. To define a loss function that can be used for training the multitask learning network, we follow candle and consider task-dependent uncertainty between the model output and the desired output of the regression task. We assumed uncertainty follows a zero-mean Gaussian distribution. For the maximum likelihood estimation, we can obtain the multitask learning loss for our regression task. For the classification task, we follow candle as well and assume that the likelihood of the output of each transmission link equals a scaled softmax function with scalar. Similarly, for the maximum likelihood estimation, we can get the loss for each encoding action task. After simplification and combination of the losses, we can obtain the multitask learning loss for our classification problem. Finally, we can formulate a single loss function as the sum of the aforementioned two functions. The weights change dynamically through the training procedure. However, small values of the sigma may cause their logarithm values to dominate the loss function and thus improperly influence the training performance. Therefore, we follow label and slightly revised loss function to mitigate the issue. Next, I will present the simulation results of our proposed method. The parameters setup is shown in the table. We apply the optimization algorithm described in System Model section to generate 1000 blocks of transmission data. For each block, the transmission between every source-destination pair contains a total of 200 time slots. Each source intends to send type 1 messages with data 7 bits per hertz per slot and the reliability requirement 70%. The type 2 messages are generated from a portion process with average rate 3 bits per hertz per slot. For the neural network, there are 4 hidden layers, and each one contains 16 neurons. The figure shows the learning curves of the multitask learning model with revised uncertainty weights. We can see that loss values reduce as the training proceeds and eventually converge to fixed values. The table shows comparison of different models. Multitask learning model with the revised uncertainty weights performs better than the other two. Single task model has the similar classification accuracy as our multitask learning model, but with much worse performance in the regression problem. Actually, the transmission power control and encoding action selection problems are strongly interrelated. Ignoring such effect can cause serious problems in transmission decision-making. In the table, we also display the ratio of successful transmissions in the training and the test experiments. Ideally, if a source chooses to send a type 1 message, it should allocate sufficient power to guarantee the transmission data rates large enough. Otherwise, transmission failure would occur, and the energy consumption is wasted. Our multitask learning model achieves more successful transmissions compared with single-task model. Finally, we compare our multitask learning-aided transmission design scheme with 3 conventional solutions. Fixed rate method intends to transmit the messages with a fixed data rate. Orthogonal transmission method orthogonalizes the message delivery process of the 2 links. Lyapunov optimization method has been introduced in the system model section, and it is the method that generates our data. Our multitask learning-aided design has similar performance as the Lyapunov optimization methods, but it outperforms the other 2. Because the spectrum resources are divided into 2 parts, the orthogonal transmission method needs large powers to ensure the message quality of service requirements, which leads to lower energy efficiency. The fixed rate scheme intends to minimize the whole power consumption. However, a low power usage does not always mean a high energy efficiency. Although our method does not perform as well as the Lyapunov scheme, our method demands much less computation time than the Lyapunov optimization method. In this paper, we consider a multi-user vehicular communication network consists of 2 source-destination links. Each link desires to communicate information with the maximum energy efficiency to potentially support multiple applications in a changing fading environment. Conventionally, to solve the formulated mixed integral optimization problem at each time slot, a time-consuming computing procedure is needed. We have proposed transforming the optimization problem into a joint classification regression problem, and then applying deep multitask learning to solve it. Simulation results have shown that our method can achieve similar performance as the mathematical optimization solution with a much faster decision-making process. Thank you for your listening. If you have any question, you can contact this email.